digital twins project, and now the presentation is already available for us. So I'm also going to talk about the scan-to-twin process, but I'm going to focus a bit more on a very small sub-step, namely the rule-based geometry extraction, which is only part of the process, obviously. So I'm starting with the motivation. Why do we actually do so? Then elaborate a little bit on the prerequisites and restrictions that this particular approach has. Talk about evaluation strategy, results, and the future work that is coming up next. So I think from the keynote we can already now be sure that everyone knows what scan-to-twin actually means. So it is the generation of as-is models based on reality capturing data. For us, it's mostly 3D point clouds coming from surveys, particularly UAV surveys. And the first question, or one question one could ask, is why don't we just mesh the instances that we actually get from the semantic segmentation? And that's a valid question because there are certainly use cases where such a mesh model, so only having instance mesh of road markings, the road surface, particular road signs, might already be sufficient. But, well, the domain of digital twins for roads is actually quite wide, and we have a lot of different domains. In particular, for traffic-related use cases, meshes are not going to be sufficient, which is why we in this work have dealt with ways to vectorize the road space. And well, this is quite useful because we can actually do some nice things with them. For example, we could derive driving directions, driving rules, and link them directly to our vectorization. So for example, a boundary line or a center line or a lane even. We can also establish predecessor-successor relations, which are useful for driving simulation. Another nice characteristic of these vectorizations is that we can relatively easily edit them. So for example, if we do scenario analysis or stuff like that, that's coming in handy as well. And the vectorization also helps us with well, another type of spatial reference via stationing over a road axis, for example, right? So in the digital twin context, that might mean that we can reference our sensors according to the axis and place them in our model like this. Okay, so our goal is to be able to derive multi-purpose, multi-scale geometric-semantic as-is models, and I hope that it's now become obvious that vectorization can actually help in this endeavor. And well, to actually tell the whole story, or at least hook into the keynote presentation we got today, here once again our concept for actually deriving the requirements of specific use cases, where the idea is that we first of all have the use case, derive some specific requirements to actually have a targeted GSM generation process, and then we can apply these requirements to our superset of extracted information to actually have a more efficient representation of the relevant items and entities for our use case. Yeah, so we are still talking about this process, but I am today focusing on the geometry extraction step. And in order to be properly able to talk about that, we first of all need some prerequisites. So obviously we need some measurement data. In this case, we conducted a case study on a German highway section using our Regal Minibooks UAV scanner, and then trained a model, particularly a point next model on a data set composed of 4 similar surveys and complemented by 6 synthetically generated point clouds to actually semantically cement the environment there. And for us right now, because we are mostly, we are right now focusing on the road space only, the most relevant classes that have been predicted by this particular model are the road markings, pavement edges, and the ground. And we can see already the performance of that model is okay-ish, but certainly not perfect, which actually leads to the question how robust of a workflow we can actually create based on semantic segmentation results, even if we know already that the quality of our semantic segmentation is not 100% accurate, right? So this actually brings me into the process of our rule-based extraction. Really the only thing else, or apart from the road marking and road surface point cloud segments, we need is a certain reference axis that might be just coming from OpenStreetMap data. In Germany, we have the Federal Topographic Cadastral Information System, which also provides these general road reference lines publicly. Or we could also apply an approach of rasterization and skeletalization to derive a relatively coarse reference axis. And after that, we can actually use this reference axis to first of all create bins along it, and then first of all analyze these bins individually by first of all identifying potential lane candidates. That works by just defining some certain range in which we laterally find road markings or pairs of road markings that could represent a lane. And in the next process step, we actually combine or match the fitting candidates of each bin along the bins to create a first estimate of the boundary lines that we actually need in our corridor. Afterwards, we can conduct a small smoothing and repair step to especially repair these discontinued boundary lines, which however are relatively close or matching in their distance to the reference line itself. And at last, we actually can derive correspondences between individual boundaries or between two boundaries, frankly, to derive the individual lanes. And that's already the vectorization step that we use. And just to show you that this is already can be quite useful, here are just, three examples mainly of derived standards or models for potential use cases where we just use this vectorization in combination with the point cloud segments to derive an IFC, a lanelet file, a CityGML file, and we also just created a mesh file. However, there's obviously some vegetation there, which in this case was manually added at this point. But the concept in general also holds place for further object groups, right? So we are also going to work on road furniture objects, such as guardrails, barriers, and stuff like this. Also dealing with civil structures and vegetation. And the idea is to aggregate all the extractable information from the point cloud data, survey data that we have available into one big set, and then apply the requirements that we have defined previously to draw the subset and generate the GSM. Okay, now very briefly to the evaluation strategy. So as I said, we initially evaluated the robustness of this very simple rule-based approach by comparing the vectorization results between ground truth labels and our point next outputs. So with the following metrics, so completeness and correctness are pretty much just another other words for precision and recall, but for our vectorizations in this case, because we compare polylines, which are boundaries, and lanes, which are polygons, with certain criteria for true positives, false negatives, and so on and so forth. And the results actually look all right, okay-ish, I would say. So in general, they are still mediocre, I would say, but comparing the actual two cases against each other shows us that the rule-based approach, pretty much matched the performance, so was robust against imperfect segmentation, which is already a good sign. And looking at the results, the primary issues that we have are actually linked to these ramp areas, right? So if we have highway intersections, they actually make a lot of the incompleteness in the vectorization step. And otherwise, the ground truth versus semantic segmentation fit match relatively well, right? So now coming to the future work. So the next obvious thing, if we wanted to keep in the track of rule-based extraction, would be using multiple axes and combining them. However, then we will have areas where they interfere with each other. So there we need some prioritization. And of course, at some point, the more complex, the larger the scale of the environment, the more non-robust it's likely going to get. So in the long run, we are planning to shift that to end-to-end data-driven approach. And therefore, the goal now is to derive a large data set which features vectorization, geometry, semantics, and topology all at the same time to allow us to analyze the potential there. Thank you very much.